So in isothermal process, what is remaining constant beta? Temperature is remaining constant. So work done in isothermal process has been calculated from the formula W is equals to integral of your P into dV. So from your ideal gas equation, PV is equals to N into R into your T. N is a constant, R is a constant, temperature is also your constant. So I can write PV is equals to your constant part of relation. So P is equals to, I can write as N into R into T divided by your volume. Okay, now substitute. I'm taking this one as equation number 1 and this one as of your equation number 2. What you do is substitute 2 in your 1. So what I'll be getting if I substitute the 2 in your 1, you see what I'll be getting right now there. W will be equal to your integral of your P value is equals to your N into R into your T divided by your V into your dV. Limits will be from V initial to your V final. So work done is equals to N R into T is a constant. Integral of your 1 by V into your dV. This is your initial volume and this one is your final volume. So W is equals to your, how much for me? N R into your T. Integral of 1 by V into dV is equals to how much beta? This will be equal to ln of your V. Limits will be from V initial to your V final. So W is equals to your N R into your T. Substitute upper minus lower limit. So it is V final minus of your ln of your V initial. So if I simplify it, we'll be getting work done is equals to your N R into T. This will be your ln of your V final divided by V initial. So work done is equals to your NR into T ln of your V final divided by V initial. V final divided by V initial. Is it clear for everyone? Clear beta? Chalo. So as P is remaining constant beta, you know from ideal gas equation as T is constant, so PV is equals to your constant. So I can write here P1 V1 is equals to P2 V2, Boyle's law. So I can write here V2 by your V1 will be equal to your P1 by your P2. So work done can also be written as W is equals to your this will be equal to your NR into T ln of your P initial divided by P final. Okay, if I remove the ln, I can write work done is equals to 2.303 NR into your T. So this will be equal to V final divided by your V initial. Or I can write work done W is equals to your 2.303 NR into T. This will be equal to P initial divided by your P final. So work done is equals to your 2.303 NRT or P initial divided by your P final. Clear, Uda? This is your work done. In isothermal process, the work done is equals to this much. If I'm applying the first law of thermodynamics beta, like say if I'm taking the graph otherwise, first we'll try to take the graph of this one. What will be the P versus V graph beta? This is your pressure versus your volume graph. So we'll be getting a rectangular hyperbola. We'll be getting a rectangular hyperbola. So if I take some point here right now, and if I draw a tangent to this one, it is making an angle theta where theta is greater than 90 degrees. So slope will be your negative. That means tan theta will be equal to your, this will be your dP divided by dV. Okay. So slope will be negative beta. M will be your negative. M will be your negative. So if I'm writing dP by dV beta from ideal gas equation theory, from PV is equals to NR into T, if I differentiate this one, using the UV rule, so P into your dV plus of your V into your dP will be equal to 0. So I can write P into dV will be equal to minus of your V into your dP. So I can write here right now, dP divided by your dV will be equal to, how much it will be better? dP by your dV will be equal to your minus of your P by V. So I can write here, therefore, tan theta will be equal to your how much? Tan theta will be equal to your minus of your P by V. That means slope of this one will be equal to how much beta? Slope of isothermal graph. Slope of your isothermal is minus of your P by V. Minus of your P by V. Slope of your isothermal is minus of your P by V. Clear? Very important beta. So tan theta is negative. That will be equal to how much for me? Minus of your P by V. Next one. Isothermal bulk modulus. Isothermal bulk modulus. Isothermal bulk modulus. That is K. Is how much? Now see, K is equals to how much beta? Volume stress divided by volume strain. Divided by your volume strain. That means K will be equal to your P divided by minus of your delta V divided by V. Okay. So that will be equal to your minus of your P. I can write as a dP divided by your dV into your V. So bulk modulus K will be equal to minus of your delta P by P will be equal to how much beta? Minus of your P by V into V. This minus will get cancelled. So K will be equal to your P. So K is what? Your isothermal bulk modulus. So isothermal bulk modulus is equals to your pressure P. So similarly, compressibility. Compressibility is right now for me your C. That is your reciprocal of your bulk modulus. Reciprocal of your bulk modulus. That means C is equals to your 1 by your K. C is equals to your 1 by your K is your compressibility. So compressibility is equals to 1 by bulk modulus, or C is equals to your 1 by K, or isothermal bulk modulus is equals to your pressure. Clear beta? Is it clear? So in isothermal bulk modulus, we got a work done, we got a graph, and we got an isothermal bulk modulus part deflation. Isothermal bulk modulus K is equals to your P, and compressibility C will be equal to your 1 by your K part of relation. Clear for everyone? Okay, beta? Now, let us try to apply the first law of thermodynamics for this one. Apply float to isothermal process. Flow to through your isothermal process here. dQ is equals to du plus of your dW. In isothermal process, temperature is constant, so internal energy will become for me how much? 0. That means dQ will be equal to your dW. dQ will be equal to your dW. Clear beta? In isothermal bulk modulus, dQ will be equal to your dW. Next one, cyclic process. In your cyclic process, if the body is coming back to the original position, then internal energy will always become how much will be beta? 0. This is your pressure. This is your volume. Okay, like say, this is your point A, this is your point B, this is point C, this is your point D. Like this. Okay, it is starting from A, and if it comes back to your A, so temperature difference will be the same. So internal energy will be equal to 0. If I apply the first law of thermodynamics, delta Q is equals to du plus of your dW. Internal energy will become for me 0. So dQ will be equal to your dW. Okay, that is dQ will be equal to your work done by gas. Work done by gas. That is dQ will be equal to integral of your P into dV I can take, or that also I can take it as of your area under your PV graph. Area under your PV graph. Clear? In a cyclic process, internal energy will become 0 beta. If I'm applying the first law of thermodynamics, float, dQ will be equal to du plus dW. So dQ will be equal to dW. So dQ will be equal to work done by gas. That is integral of P into dV, or that is also equal to your area under your PV graph. Area under your PV graph. Clear, beta? Sure. Next one is specific heat. Next one is your specific heat. Represented by letter S. Specific heat represented by your S. So what is the specific heat formula, beta? Can anyone tell me? For your m gram of your gas, if I am calculating, what is this one? Q will be equal to your m into S into your delta T. Or else I can write specific heat S will be equal to your Q divided by m into S. S I have already taken here right now, so it will be your delta T. It will be your delta T. Temperature difference. So S will be equal to your Q divided by your m. S will be equal to your Q divided by your m. Here m is equals to your 1 gram beta. Okay. Anyone can tell me the units for this one? In CGS system, it is calorie divided by your gram degree centigrade. Or in SI system, it can be taken as of your joule divided by your kg degree centigrade, or I can take it as of your Kelvin. No problem. Okay. The next one is molar specific heat. Next one is molar specific heat. Okay. Next one is your molar specific heat, represented by letter capital C. Okay. Molar specific heat is for what, beta? 1 gram mole per 1 gram mole. If I'm talking about for your 1 gram mole, I can write for gas, Q will be equal to N into S into your delta T. So no, so not S, it is represented by C, sorry. N into your C. N is number of moles into C is specific heat into your temperature difference delta T. That means C will be equal to molar specific heat is equals to Q divided by N into your delta T. So C is equals to your Q divided by your N into your delta T. C is equals to your Q divided by N into your delta T part of relation. So what N is nothing but what, beta? Number of moles. N is equals to your number of your moles. That is equals to your 1 mole, I can say. Okay. Unit will be equal to, what will be the unit, beta? Calorie per number of moles, mole degree centigrade, or Kelvin you can take it out, no problem. Okay. Molar specific heat is of two types, beta. C is of your two types. One is your CV, another one is your CP. CV is known as molar specific heat at constant volume. Molar specific heat at your constant volume. CP is equals to your molar specific heat at constant pressure. At a constant pressure. Okay. So C is equals to your molar specific heat. We are having two types of the molar specific heat, beta. One is your molar specific heat at your constant pressure. Another one is a molar specific heat at your constant pressure. Now, for adiabatic process, delta Q is how much, beta? 0. For adiabatic process, delta Q is equals to 0. So what will be the molar specific heat, beta? C is equals to your delta Q divided by your N into your delta T. So it is 0 divided by N into delta T. So that will be equal to 0. So molar specific heat is equals to 0 for your adiabatic process. Next one. Relation between S and C. Specific heat and molar specific heat participation. So if I'm talking about your relation between your S and your C. S and as well as of your C. See here, right? Q is equal to how much, beta? M into S into your delta T. Similarly, Q is equals to your N into your C into your delta T. So therefore, equating both of them, MS into your delta T will be equal to your N into C into your delta T. So this delta T will get cancelled. M into your S will be equal to your N into C. So if I'm taking here M into your S divided by your N is equals to your C. M by N is nothing but what? Molar specific heat, but a molecular mass. It is your M naught into your S is equals to C. That means molar specific heat is equals to your molecular weight or molecular weight into your S part definition. So what is your M here right now, beta? Molar mass. I can write this one as of your molar mass. Very important, beta. Relation between the specific heat and as well as of your molar specific heat, M naught into S will be equal to your C part relation. Okay. Generally, for any process when we are writing, generally for any process we are writing, molar specific heat of your process will be equal to your delta Q divided by N into your delta T of your process. C of your process is equals to your delta Q into your N divided by delta T of your process part of relation. Clear, beta? For any process, like say if I'm taking the CV process, constant volume. That means CV, molar specific heat at your constant volume. Apply the first law of thermodynamics and get me the volume formula for this one, beta. Okay, so from first law of thermodynamics, dq will be equal to your du plus dw. As it is a constant volume, so work done will become for me 0. So dq will be equal to your du. So dq will be equal to how much, beta? dq will be equal to your N into your C into your at your constant volume into your dt will be equal to your F by 2 into N into R into your dt. Anything is getting cancelled in this one, you see, beta? This delta T, this N and this N will get cancelled. So from this one, I can write CV will be equal to how much for me? CV is equals to your F by 2 into your R. Okay, F by 2 into your R. So molar specific heat at your constant volume will be equal to how much for me, beta? F by 2 into your R. What do you mean by F, beta? F is nothing but of your degrees of your freedom. Degrees of your freedom per definition. Clear? So if I'm talking about for monoatomic gas, for monoatomic gas, Cv will be equal to your 3R by 2. For your diatomic gas, Cp will be equal to your 5R divided by your 2. 5R divided by 2. That is at your constant volume. In the same way, if I am talking about it constant pressure, I'm talking about at your constant pressure, molar specific heat at your constant pressure, molar specificated constant pressure, that is your Cp. So if I'm writing the value of your Cp by definition, beta, see here, how do you write this one? From the first law of thermodynamics, if I'm writing, from dq is equals to du plus dw, beta. So dq is equals to how much? N into Cp into your dt, that is equals to your F by 2 into Nr into your dt, plus work done will be equal to your P into your dV. So I can write this one as N into Cp into your dt will be equal to your F by 2 Nr into your dt, plus from ideal gas equation, P into delta V can be written as of your Nr into your dt. This dt, and this dt will get cancelled. Number of moles will also get cancelled. So Cp will be equal to your F by 2 into your R plus of your R. So I can write like this. Okay. R, I can even write like this. Cp is equals to your F by 2 plus 1 into your R. Okay. Or else if I rearrange and write it out, I can even write this one something like this. Cp is equals to F by 2 R will be equal to how much you see, beta? See here. F by 2 into R is Cv, molar specific heat at a constant volume. So this will be your Cv plus of your R. So from this one, I can write Cp minus of Cv is also equal to capital R. Okay. This one is known as of your Mayer's formula. Okay, Mayer's formula. Cp minus Cv is equals to your R is your Mayer's formula per definition. Clear for everyone, beta? Okay, so Cp is equals to your F by 2 plus 1 into your R. Clear? Now, if I'm taking the ratio of Cp by Cv, what will be the ratio, beta? Ratio of Cp and Cv. Ratio of your Cp and Cv. What will be that one? Cp divided by Cv will be equal to your F plus 2 divided by 2 into your R divided by, this will be your F by 2 into your R. R gets cancelled. 2 and 2 will get cancelled. So this will be your F plus 2 divided by F. That means it will be equal to your 1 plus 2 by F. That means Cp by Cv is gamma. So gamma is equals to 1 plus of your 2 by your F. This is the relation. Clear, beta? So gamma is equals to your that much. That means gamma value is equals to how much for me? What is Cp by your Cv? Gamma is equals to your Cp by your Cv part. Or I can write this one as of your gamma is equals to your gamma is equals to your. If I'm taking this one here right now, this will become for me how much? F by 2. So this one is nothing but of your F plus 2 divided by your F is equals to your gamma. For monoatomic gas, if I'm writing for your monoatomic gas, gamma value will be equal to how much for me, beta? For monoatomic gas, F is equals to 3. So therefore, gamma is equals to your 3 plus 2 divided by 3. So that will be equal to your 5 by 3. For your diatomic gas, if I'm writing, for your diatomic gas, F is equals to your 5. So gamma is equals to your 5 plus 2 divided by 5. That will be equal to 7 by 5. Clear, beta? Standard values. Next one. As F plus 2 divided by your F is equals to gamma, I can write here F plus 2 is equals to your gamma times of your F. So F will be equal to how much, beta? 2 divided by your gamma minus 1. So F is equals to your 2 divided by your gamma minus of your 1. So therefore I can write CV is equals to, CV is equals to how much for me? F by 2 into R beta. C by 2 is your F by 2 into your R. That means that can be written as of your, this will become for me your R by your gamma minus 1. So CV value can be written in terms of gamma as of your R. So CP value will be equal to your CV plus of your R. So that will be equal to R by gamma minus 1 plus of your Kepler. So that will be equal to your, this will be the LCM gamma. This will be equal to your R. That means this will become for me gamma times of R. So CP value in terms of your gamma will be equal to how much for me? Gamma into your R divided by your gamma minus of your 1 part, or gamma into R. Very important relation, brother. CV in terms of gamma and CP in terms of your gamma part of relation. Okay. So in the same way, if I'm talking about internal energy, what is an internal energy formula, beta? Delta U is equals to your F by 2 into N into your R into your delta T. So I can write internal energy is also equal to your, this is your N into F by 2 into R can be written as of your CV into your delta T. So delta U will be written as of your N into your CV into your dt. Or else I can even write delta U is equals to your N, CV will be equal to how much, beta? R into your delta T divided by your gamma minus 1. So internal energy in terms of your gamma, if I'm writing, that will be equal to your N into R into delta T divided by your gamma minus 1 part of relation. Clear for everyone? Okay. So just let me share you with another file. Is it getting shared, beta? Are you able to see the screen? Anyone please respond? Nandini? Yes, sir. Okay, chalo. See this question, beta. In an isothermal reversible expansion, if the volume of 96 gram of oxygen at 27 degrees centigrade is increased from 70 liters to 140 liters, then work done by the gas will be equal to how much? Can anyone try better this? Isothermal process. That means the temperature is remaining for me constant. If temperature is remaining constant, work done will be equal to how much? N into R into T. So this one is of your log of your E into your V2 divided by V1. N will be equal to your mass by your molecular weight into your R into T. This will be log of your E. This will be your V2 divided by V1. If I remove the log, I can write this one as a 2.3 into your M divided by capital M R into T. This is a log to the base of your 10 into your V2 divided by your V1. So number of moles is right now for me mass. Mass is given how much in the problem, beta? 96 divided by which gas it is? Oxygen. Oxygen is equal to how much for me, beta? 32 into your R value is equal to how much for me? You will be getting the answer in terms of R only. Okay, I'll keep in terms of R into temperature is 273. That means T is equals to 27 plus 273. That means it will be a 300 Kelvin. So into your 300 Kelvin, this will be the log to the base of 10, 140 divided by your 70. So this one and this one will get cancelled. 7 ones are 7 twos are. So that will be equal to 2.3 into your 9.6 divided by 96. So that will be equal to your 96 into your R divided by 32 into your 300 into log to the base 10 of your 2. So let's simplify and tell me what will be the answer for this one. Answer is in terms of log to the base of your 10 only. So it is in terms of your log. 2.3, it will be your log to the base 10 into T. That means this one is R as usual it is there. 32, 96 into your 32. How much it will be beta? 900. Yeah. So fourth option will be the answer. Clear beta? This one is 3, isn't it? Clear? Sure. Next one. A thermally insulated cylinder is divided into two parts by your screen. A thermally insulated container is divided into two parts by a screen. One part, the pressure and temperature are P and T for an ideal gas filled. The second part, it is a vacuum. If now a small hole has been created in the screen, then the temperature of the gas will be equal to how much? And thermally insulated container beta. Thermally insulated container means there is no transfer of your temperature. So free in this case of beta on free expansion gas, in free expansion, there will be no change in internal energy. Internal energy will become for me 0. That means temperature remains the same. Temperature remains the same. So it will remain same beta. Third option will be the answer. Because it is thermally insulated, na beta. So it will be a free gas. So it will be your free gas. There will be your free expansion. There will be your free expansion of gas. For free expansion of a gas, there is no change in temperature difference. So internal energy will become 0. Next one. 540 calorie of heat has been converted into 1 cubic centimeter of water at 100 degrees centigrade into 1671 cubic centimeter of steam at 100 degrees centigrade at a pressure of 1 atmosphere. The work done against the atmospheric pressure nearly is equals to how much? Directly work done formula beta. Amount of the heat is given how much for me? 540 calorie. So amount of your heat is given how much for me? Your Q is equals to your 540 calories. Change in volume is equals to how much for me beta? 100 degrees centigrade. Centimeter of your water from your 100 degrees centigrade. How much I am getting beta? Into 161 cubic centimeter of steam at your 100 degrees centigrade. So I'll take this one approximately for the calculation purpose 1670. Atmospheric pressure will be equal to how much better? 10 to the power of 5 pascals or Newton per meter square. Or that can be taken as 10 to the power of 6 dyne per centimeter square. So he's asking work done against the pressure. So it is P into your delta V. So P will be equal to 1.01 into 10 to the power of 6 into. This one is 1670 divided by your. In calories we are taking right now. So this will be equal to 540 calories. So that will be equal to 4.2 into 10 to the power of 7. So that will give me the answer for this. I can just calculate it basically. How much are you getting meter? Approximately you can tell. This 10 power 6 will go and this one will go here right now. This 0 and this 0 will also go right now there. So it is 1.01 is nothing but approximately 1 into 167 divided by your 4.2. That means this will become for me 1670 divided by 42. Approximately 4, that means 40. Okay, approximately I can take it as of your 40 calories. So next one. Sudden bursting adiabatic, we have not done this one, but we'll do it later. During adiabatic expansion, this also I have not done it. 1 mole of helium, this is also an adiabatic. Okay, a gas expands under a constant pressure P from V1 to V2. The work done by the gas will be equal to how much? Can anyone do this one better? A gas expands under a constant pressure. Constant pressure means isobaric. From V1 to V2, the work done will be equal to how much? Work done will be equal to P into your delta V. So that will be equal to P into your V2 minus of your V1. P into your V2 minus of your V1. That means A will be the answer for this. Okay, next one. A gas is being compressed at a constant pressure of 50 Newton per meter square. This should be capital N beta. Newton per meter square from a volume of 10 meter cube to a volume of 4 meter cube. Energy of 100 joule is added to the gas by its heating. Its internal energy will be equal to how much? Apply the first law of thermodynamics beta. From your first law of thermodynamics, I can say that delta Q will be equal to your delta U plus of your delta W. So that means that this will be equal to delta U plus pressure into change in volume. So delta U is equal to how much for me? 100. So he's asking us internal energy. Delta U plus of your pressure is your 50. Change in volume will be equal to how much beta? From where to where? V2 to your 100, 10 to your volume of V3. That means this will be equal to your 4 minus of your 10. Okay, so that will be come out for me how much you see. So this will be your delta U will be equal to 6. How much beta? 400. 400 joules, because we'll be getting negative. This will negative, negative, negative will get cancelled. So delta U is equals to done beta. $400 it increases by 400 joules. We have not done still this one. Okay, this one can you do beta? An ideal gas has a volume of your V naught. An ideal gas has a volume of V naught at 27 degrees centigrade. It is heated at a constant pressure. Constant pressure means isobaric. So its volume becomes 2V naught. So final temperature will be equal to how much? So from ideal gas equation, PV is equals to nRT. Pressure is remaining constant. PV is equals to N into R into T. Pressure is constant, so V is directly proportional to your temperature. So I can write here V1 by your V2 is equals to your T1 divided by your T2. V1 by V2 is equals to your T1 divided by T2. So an ideal gas has a volume of V naught. This one is having a volume of V naught at 27 degrees centigrade. It is heated to a constant pressure, so that its volume becomes 2V naught. Okay. So V1 is V naught, V2 is your 2 times of V naught. Temperature is your 300 divided by your T2. This one and this one will get cancelled. So T2 will be equal to your 300 into 2. So that will be equal to your 600 Kelvin. So 600 Kelvin is not there. So I can write this one as of your 600 minus of your 273. How much it is? 327. Done, madam? Sure. Next one. When an ideal gas in a cylinder was being compressed isothermally by a piston, the work done on the gas was found to be 1.5 into 10 to the power of 4 joule. During this process, about 3.6 into 10 to the power of 3 calorie of heat is being flown out of the gas. 3.6 into 10 to the power of 3 calorie of heat has been flowed into the gas. 1.5 into 10 to the power of 4 calorie of heat has been flowed into the glass. 1.5 into 10 to the power of 4 calorie of heat has been flown out of your gas. Okay, if I'm using the isothermal compression beta, there is always increase in the heat, which must be saying that there will be flow of a gas. That means if I'm using the first law of thermodynamics, delta Q is equals to delta U plus of your delta W. Internal energy will be equal to 0 because it is compressed isothermally. There is no change in temperature. So delta Q will be equal to your how much? See, when you compress this, there is always an increase of your heat beta. That means which will be flowing out of the gas. So when it is flowing out of the gas, delta Q will be equal to how much beta? Delta W. Okay. So when you are compressing it, volume is decreasing. That means delta Q will be equal to your minus of your 1.5 into 10 to the power of 4 joules. If I'm writing in terms of calories, it is 1.5 into 10 to the power of 4 divided by your 4.2 approximately. That will give me in calories. So that will come out for me minus of 3.6 into 10 to the power of 3 calories. So minus sign indicates that heat is being flown out of your gas. There, beta? Sure. Next one. 1 mole of an ideal gas expands at a constant temperature at 300 Kelvin from an initial volume of 10 liters to the final volume of 20 liters. The work done, constant temperature means what type of a process beta? Isothermal process. So work done in isothermal process is equals to your NR into T. This one is log of your E, V2 divided by your V1. So that will be equal to your 2.3. I can write here right now. In terms of your log E, if I'm writing the relation right now. So this will be equal to how much for me? 2.3 into your number of moles is equals to how much for me? 1 into your R value is 8.3 into temperature is 300 Kelvin. Directly it is given into your log to the base of your 10 into V2 by your V1. So it is 20 divided by 10. So this one and this one will get cancelled. So it is approximately 2.3 into 1 into your 8.3 into your 300 into log of your 10, log to the base 10 of your 2. Simplify it, we'll see how much I'm getting the answer for this. Two 2.3 means 23 by 10 into 83 divided by 10 into. So this 2 will be getting cancelled. 3 into log to the base 10 of your 2. How much are you getting, beta? Option B. Very good. It is approximately 1728 joules. Done? Sure. Next one, bro. The vessel contains 5 liters of a gas at 0.8 meter. Pressure is connected to an evacuated vessel of volume 3 liters. The resulting pressure will be how much? Assuming that the whole system to be an isolated. So how much amount beta? A vessel contains 8 liters of volume at 0.8 meters. That means 0.8 into your 5 will be equal to your pressure into your. This will be equal to how much for me? 3 plus 5. P into your V. Simplify it. Pressure into your volume. Pressure into your volume. Pressure is directly proportional to what beta? Pressure is being connected. That is how much for me? 0.8 meters of your atmospheric pressure. Okay. So it is 0.8 into 5 is equals to P. So this one is your 8 divided by 10 into your 5 is equals to your P into your 8. So this one and this one get cancelled. 5 ones are 5 twos are. So P will be equal to 1 by 2. That means that will be equal to your 0.5 meters. B will be the answer to this. Clear, beta? I hope we can do this one. How much work is to be done by decreasing the volume of an ideal gas by an amount of 2.4 into 10 to the power of minus 4 meter cube at normal temperature and constant normal pressure of 1 into 10 to the power of 5. How much work is asking? That means at a constant pressure, work done will be equal to your pressure into change in volume. So that will be equal to your PV is equal to your N into R into your delta T. Number of moles is 1, R value is your 8.3 into temperature difference is your 100. So that will be equal to your 83. So it will be equal to your 830 approximately, isn't it? 830, approximately 830. 830 means I can write how much right now, beta? Is asking right now how much for me? NRT 8.3. So what I'm doing now? Work done na, is given for me the data. How much work is to be done to decrease the volume of an ideal gas by an amount of your 2.4 into 10 to the power of your minus 4. That means I can use the relation work done will be equal to your pressure into change in volume. He's asking work done only. No? So how much is the pressure given for me? Ideal gas by an amount of normal temperature and constant of normal pressure. Okay, volume is given for me and pressure is given for me. Pressure is 1 into 10 to the power of 5 into volume is 2.4 into 10 to the power of minus 4. That means this will be 10 to the power of 5 into 24 divided by 10 into 10 to the power of minus 4. That means this one, and this one will get cancelled. So this will be your 24 joules. D must be the answer. Next one. A container having 1 mole of your gas at a temperature of 27 degrees centigrade have a movable piston which maintains at a constant temperature in a container of 1 atmosphere. The gas is compressed until the temperature becomes 127 degrees. The work done by this one will be equal to your how much? Okay. Constant pressure. So at constant pressure, if I'm writing, work done will be equal to your P into your delta V. That is equals to your NR into your delta T. Number of moles is your 1. R value is your 8.31 into temperature difference is 100. That means it is your 83 divided by 10 into your 100. This one will get cancelled. So this will be equal to your 830 joules. 830 joules means nearby answer I can write as of your 840. In the reversible isochoric change part of relation. That means in isochoric reversible delta V is equals to 0. So work done is equals to P into delta V. So that is your 0. So work done will be equal to your 0. And we have got right now the adiabatic process and heat engines that we'll try to do it in the tomorrow session of your class paper. Okay? Sure. Take care. Bye.